All right, so in this part of the lecture, we're going to talk about relative motion, which basically covers how we describe velocity. Because when we talk about velocity, so technically there is no such thing as true velocity or absolute velocity. Because when we talk about velocity of some object is 15 meter per second, for example, right there, right? So this 15 meter per second is measured by some observer. But maybe, for example, so that's could be like velocity measured by one observer, like here, like Emmy. But the Carlos, for example, if he measures the velocity of the car, whatever Emmy measured to be 15 meter per second, Carlos can actually measure something different. All right. So that means what we're going to do here is we're going to find out how we can take a velocity of the object and measure it, but such that to really represent a velocity, you need to have a velocity relative to something else or someone else. So that's why, the term relative velocity, because whenever we are given velocity, it has to be relative to, very specific observer, for example. So that's why what we do here is this. So you have, we're going to use A for Amy, C for Carlos, and B for Bill. All right. And what I have here is when you talking about Amy, who technically is at rest, standing there, when she measures the velocity of Carlos, she will measure the velocity to be 5 meters per second. But then we can write this in terms of to make it specific that this is what Amy is measuring. We can say that velocity of Carlos relative to Amy, to the subscript, velocity of whatever relative to the very specific observer. So velocity of Carlos relative to Emmy is then plus 5 meters per second I hat, for example. Then same way, velocity of Bill relative to like Emmy will be 15 meters per second. All right. Now, equally, Carlos and Bill can actually measure the velocity of Emmy, which then they can imagine that, well, I'm not moving, she is moving. So then what they can do, they can say that the velocity of Emmy relative to Carlos is basically Carlos is at rest and Emmy is moving 5 meters per second, but is moving 5 meters per second in negative direction. Same way you can say the velocity of Emmy relative to Bill will be then negative 15 meters per second. Because if you're in a car, it seems like you're not moving, but Emmy is moving, but in the opposite direction. So you can always say this, right? Velocity of, so let's say velocity of 1 relative to 2 is always negative of velocity of 2 relative to 1. That's always going to be true. Okay. Now, the difficulty comes in when, for example, we want to find what is the velocity of Carlos relative to Bill, or what is the velocity of Bill relative to Carlos. Well, they are moving relative to one another, and their velocity is not same as the, Emmy would measure. So this is why we're going to find out that there is a method. There's like a template that we can use to calculate the velocity relative to, different observers. So let's say velocity of the Bill relative to Emmy, or velocity of the Bill relative to Carlos, or velocity of Carlos relative to Bill, and so on and so forth. All right. So the way the notation goes like this. So you can see, right? We are looking at how to calculate velocity of Carlos relative to Bill. And in our, let's say calculation, we're going to involve 3 observers. So Emmy, Carlos, and Bill. Because in order for us to actually use this template, we need 3 observers, or 3 objects, or 3 persons, let's say. So in this case, what we do, you can see, right? There are 2 subscripts for each term, and the velocity of Carlos relative to Bill can involve sum of 2 other velocities. It's always going to be like that. It's sum of 2 other velocities. Now, that means you have first term added to the second term. That means one velocity added to another velocity to get the velocity of the Carlos relative to Bill. And the notation, the template goes like this. So the first subscript of the first term on the right side should be the same as the first subscript of the, the velocity on the left side. And then the last subscript of the second term on the right side should match the, last subscript of the term on the left side. All right, so you can see like that. And then the subscript between, right? So let's say between those two, which is the second in the first term or the first in the second term on the right side, should be the one that is not being used. Oh, sorry, which is here. See, on the left side, you have C and B, but we're not using A, but A is being used by those two velocities on the right side. Again, you can see, right? So write down velocity of the Carlos relative to Bill, can involve velocity of the, move it here, Carlos, relative now to the one that is not part of the combination on the left side, which is Emmy, then plus velocity of Emmy, those match, then relative to Bill. All right, so that's what we're gonna do. So velocity of Carlos relative to Bill gonna equals to velocity of Carlos relative to Emmy, which we assume to be 5 meters per second, then plus velocity of Emmy relative to Bill, which remember was then negative 15 meters per second. So then velocity of Carlos relative to Bill is negative 10 meters per second. So we didn't have to guess anything, we could actually calculate. And you can see that if you go back, that's what we have, right? Carlos moving to the right at 5 meters per second, Bill moving to the right at 15 meters per second. So then relative to Bill, Carlos is actually moving back at 10 meters per second because Bill moving faster than Carlos. So it seems like Carlos is actually moving backward, but 10 meters per second. All right, so the same thing we can say, for example, velocity of the, let's say, Bill relative to Carlos, for example. What will this be? Well, this will be then, again, using the same template, it will be velocity of Bill relative to whatever not combination of this one, which means Emmy, plus then velocity of, Emmy relative to, this moves here, Carlos. So let's see what we get. VBA, right, velocity of Bill relative to Emmy is 15 meters per second, plus velocity of Emmy relative to Carlos is then negative 5 meters per second. That means Bill moving relative to Carlos at 10 meters per second I have, which, again, should make sense. All right, so that's kind of like what we have. That's, that's the rule for the notation. So try to kind of like, look at it and, maybe like try to understand that. All right. Well, same way we can also look at it in terms of position, right? So let's say, imagine you have Carlos and Emmy, for example, measuring position of something. Well, then they might measure it differently because, they have different position relative to that object. For example, if Carlos is closer to the object, he might measure, let's say a less distance, right? So I guess here, so we have Emmy and Bill, for example. So Emmy will measure the position of Carlos to be different than Bill will be because Emmy is closer. So this will be, different. So that you can say that position of Carlos relative to Bill, again, it's the same subscripts, right? Is, position of Carlos relative to Emmy plus position of Emmy relative to Bill. So the same kind of like the template for the position as well. These are known as technically as Galilean transformation. So we're using the Galilean transformation to find velocity and position. All right. So you can say Galilean transformation of velocity, which is, again, same basically the notation. Velocity of Carlos relative to Bill equals velocity of Carlos relative to Emmy plus velocity of Emmy relative to Bill. Again, the first one should be, first on the left should be the first on the first term on the right. The second one on the left should be the very last one of the second term on the right. And those inner ones, right, should be representing the third observer, which is not part of the, calculation on the left side. All right, anyway, a little of practice will make this relatively straightforward. Let's look at this example here. A boat's speed in still water is given as velocity of boat relative to water as 1.85 meter per second. Now, think like this. Here we have a river and water, right? So if you have a boat, then can move in water at the speed of 1.85 meter per second. Now, if the boat is to travel directly across the river, whose current has a speed of velocity of water relative to the shore as 1.2 meter per second, at what upstream angle must the boat head? So think like this. So here's the river, and let me talk about, like, let's say this is point A, this is point B, two positions, right? So the boat, if goes straight like this, so velocity of the boat relative to water, which is 1.85 meter per second. Let's call this J hat because it's vertical. Think like this. If it's moving straight like that, and if there is no current, it can technically go and reach point B. But what we have is this. All right. So what we have this, the velocity of the current, which is basically in this direction, right? Velocity of the water relative to the shore, will make then this boat move like this instead. And then it will go and get to this position C instead of position B, all right? That means in order to avoid that, what we're gonna do here is gonna be, understand that the left current, the current that is to the left, gonna make the boat move toward the left. So instead, we're gonna have the boat move at some angle, theta, with respect to that, straight line from A to B. So then even if there's a current, making it kind of like move toward to the left, this gonna make the boat itself technically then move in a straight line from A to B. And that's what we want to know. What should be that theta with respect to the normal, right? The straight line, so that the boat will move relative to water. So then eventually the current effect is, neglected, and it goes from A to B directly. All right. So then technically you can say, right, we end up with this triangle. Okay. So what we want to find is what should be the velocity, the theta be, right? So let's say we want to find the theta. Okay. To find the theta, then what we have here is this. So we have a triangle, and the triangle said that this is the velocity of boat relative to the shore. This is the velocity of the boat relative to the water. This is the velocity of the water relative to the shore. And you have that triangle over there. Then theta is technically then can be calculated using those sides. So we are given that this is 1.85 meter per second, which is technically the hypotenuse. And then this has 1.2 meter per second, which is then opposite. That means we can use those information, right, to find, velocity, or just the angle, right, of that, that boat makes with the normal, let's say. All right. So understanding that we are dealing with hypotenuse and opposite sides, so we can use sine of theta, which is opposite over hypotenuse, which means opposite is the velocity of the, or the speed of the water with respect to the shore, which is 1.2 meter per second, and the hypotenuse is basically 1.85 meter per second. Okay, so this is going to give us 0.65, let's say, and then finding the theta, which is inverse sine of 0.65, we'll then get 40.4 degree angle. That means the boat has to have 40.4 degree basically east of north, right, in order to actually be able to go in a straight line toward north, right, from point A to B. All right. Then we have this. So the same boat now heads directly across the river. I guess he didn't listen to us, so he decided to go directly across. So then whose current is still 1.2 meter per second. What is the velocity, magnitude, and direction of the boat relative to the shore then? Okay. So and if the river is 110 meter wide, how long will it take to cross, and how far downstream will the boat be then? Right, as I said, right? So let's say this is being point A, this is being point B, then it's gonna go and reach some point C, right? So then what we want to know here is this. Again, so we have this velocity of the boat relative to the water is 1.85 meter per second, J hat. Velocity of the water relative to the shore is then 1.2 meter per second, negative I hat, right? And what we want to know here is, let's say we're given that the river is 110 meter wide. That means this distance here, right, is 110 meters. Okay. So here's then what we do. for this problem, we basically approach the same way. That means we want to know what is the velocity of the boat relative to the shore. Okay, that means I want to find velocity of the boat relative to the shore. Well, this will be sum of two different velocities, right? Again. And remember, this should be the first one here, and that should be the last one over there. Which means between them, right, I have to put the third one, which is not part of this, and that's basically water, right? So velocity of the boat relative to water plus velocity of the water relative to the shore, okay? So then this is basically 1.85 meter per second, J hat. And this is then minus 1.2 meter per second, I hat. Or you can say velocity of the boat relative to the shore is negative 1.2 meter per second, I hat, plus 1.85 meter per second, J hat. Well, from here, then I can calculate, because they're I hat, J hat, I can calculate the magnitude, which will be 1.2 square plus 1.85 square, which will give me 2.21 meter per second. And then I will find inverse tangent of like 1.85 over negative 1.2. And this will give me then negative 33 degrees, which means, let me see. Sorry, guys, actually other way around, right? So what I have here is, this one is velocity of the water relative. So this is negative 1.2, and the 1.85 then will be the adjacent side. So that's how I'll do it. All right. So then if I do this calculation, right? If I basically do this, so let's see. Negative 1.2 divided by 1.85. I'm going to get negative 32.9, which is basically negative 33. Right. So, which is basically then angle that it will make, right? So let's say 32 degrees. So this will be then, let's say 33 degrees, like that. Okay. So then, what do we do from here? That was basically the part A, right? So then for part B, it says, if the river is 110 meter wide, how long will it take to cross, and how far downstream will the boat be then? All right. So for this, let's say if I want to find the time, that means, I can just say, okay, so the time, I can just calculate from looking at how it goes, that's 110 meters. So then what is the velocity that it has going through that distance? Well, it's this one, velocity of the boat relative to water, right? Because that's the velocity it has going in that 110 meter distance, because the 110 meters is the vertical distance, and you need vertical velocity, which is basically J hat velocity, and that's 1.85. So you can say that delta Y is equals to V times T, right? Or then time is equal to then delta Y over V. So this is like vertical velocity, right? So 110 meters divided by 1.85 meter per second. And we're going to get then 59.5 seconds. That's how long, roughly 60 seconds. That's how long it's going to take. All right. Now, that means same thing, same time going to be for the going from the, this distance, which is, in terms of the horizontal component of this velocity, which is this guy here, 1.2 meter per second. So then I can say then this distance from B to C, right, the CB distance, right, which is, let's say, delta X, is nothing but Vx, which is, 1.2 times the time of, 59.5. That means it's going to be roughly 71 meters from the point B, relative to, let's say, this point B, right? If the, boat is actually heading 32 degree in that direction with that speed. So it's going to be 71 meters away from where it wanted to be technically.